So today we're talking about nutrient cycles. Those are different from energy flow because energy starts from the sun and it goes to the producers and then the consumers, and at each step you lose energy. It's not destroyed, but it dissipates, it spreads out, and you never get to see it again. Nutrients are different though. Nutrients are things like carbon, phosphorus, nitrogen. These are things that cycle through the environment. So let me show you a picture of that. So here's some plants, some producers, and they have carbon in them, let's say, or let's go with nitrogen. So they've got nitrogen in them. The nitrogen gets into the mice or the herbivores when the mice eat the plants, and so the nitrogen moves here. When those poop or when they get eaten, when they poop, the nitrogen goes to decomposers. When they get eaten, the nitrogen goes into the carnivores, and then when they die or poop, the nitrogen is taken up by the bacteria or the fungi, the decomposers, and then that nitrogen is available again to the plants. So the nutrients cycle around and around and around. The nutrients that are here today in the environment are pretty much the same as the ones that have been on this planet for forever, except for some radioactive stuff. So the nitrogen in you is the same nitrogen that might have been in dinosaurs.
Except for the radioactive material.
Yes, except for this. Okay, so cycles of matter, we're going to look at carbon, nitrogen, and we'll look at water too. Essentially, all of the atoms on Earth will stay the same for the life of our planet, except for radioactive stuff.
Oh, wait, I think so.
However, they can be recycled, combining in different ways with other atoms.
What is it, Anna?
So the carbon cycle, we're going to look at carbon first. Here's carbon dioxide gas, that's in the atmosphere, and that's taken into plants when they do photosynthesis. So the equation for photosynthesis is something you should know. So my son David's helping me today. David, say hi to all the kids.
Hello.
So here's the equation for photosynthesis. Do you know what plants make, David?
They make light glucose.
They make glucose. Excellent.
And I think, oh gosh.
Well, let's figure this out. Hold on.
And also carbon. Not
Whoa,
carbon. CO2.
No, wait. Glucose is C6H what? Do you remember?
12.
Excellent.
Yeah.
C6H12. Is there anything else?
And then I think it's O6.
Yeah. C6H12O6. So here's glucose. So that was pretty good, Davey. So where's the carbon come from? Where did the plants get their carbon?
Well, I think they have breathing holes on the inside of their leaves.
They do.
They might
little
get it from the
stomata.
ground.
They don't get it from the ground. They get it from the air.
All right.
And so what's the carbon that's in the air?
The carbon in the air, I think, is probably from water.
And it's not, because that's H2O.
Oh, well, that's where they get the hydrogen.
That it is. So let's talk about the carbon.
The carbon, they probably get...
Where do they get that carbon?
Oh,
you said it already.
CO2.
So you wanted to put that CO2 on the wrong side of the equation. So when I write the photosynthesis equation, I'll say, what are we making?
Right, people, I always forget.
Well, I say, what are we making? And look, there's carbon here. I must have gotten that carbon from somewhere. I got it from CO2. Oops. So here's carbon dioxide in the environment, in the atmosphere, and I'm running out of space, but where do they get their hydrogen, Davey?
They get their hydrogen from water.
Beautiful. So I'm going to just write that over here.
Oh, and then they make the byproduct of oxygen.
Excellent. So if we do a nice job and put in our numbers in front of these, we would get 6 waters. So that would give you the 12 H's with the 6 times 2 would be 12. And then you actually get 6 carbon dioxides, and I'm supposed to put that in front, but I don't have any space. So there's my 6 carbon dioxides. And if you count up all the O's, that's 12 plus 6. We've got some extra O's. So they make, oxygen.
O2 actually.
Yeah, that's the stuff in the environment. And can you tell me how many?
Let me just think about this for a second. So
think it out loud.
Right, so there's 6 CO2s, so then that means there's 12 oxygens off of that, so that completely covers the, oh wait, no, actually, I was looking at the hydrogen, that double covers the oxygen, so there's 6 left over, and then there's 6 extra O's, so there's 12, well, actually, no, there's only 6 O2s because there's 2. Oh.
Good, so there's 12 O's, but since it's O2, that gives us 6 O's. So anyway, this is the equation for photosynthesis.
Actually, I have a kind of question. Do they ever lose hydrogen through this cycle?
Like, they do, and so, yeah, photosynthesis is a really, this is the overall equation. There are about 1 million little reactions that happen in between starting stuff and ending stuff. I don't know that it would go
because I just heard that it's hard to get hydrogen back into the environment, so I just...
So they do, they will hydrolyze the water. There's one other thing we should put in here, though, one other important thing. Do you get fat from drinking water and eat and breathe in carbon dioxide?
Um.
Could you breathe all day and drink water all day and still be hungry?
Well, yes, it's because it's the chemical bonds lock energy inside of the
Well, what about glucose? Could you eat
yes, glucose? They lock energy inside of the chemical bonds between like the 6-12.
Oh, he's so good, isn't he? Okay,
we just learned about this as well, not really just learned about this, but
yay.
Seeing as how it's after the school year for my school.
So this has all kinds of energy, yes?
Yep.
And so how do plants get their energy to put this stuff together?
From the sun.
Oh, he's so good, isn't he? So it could be from the sun, or it could be from a light lamp, some kind of...
A lamp gets actually the energy from the sun if you...
That's true, because... Go ahead, tell us.
Well, actually, they might not get it from the sun. They can either get it from wind or the sun, because if they're burning coal, then that originally was from plants. If they're burning, like, petroleum or whatever, that's also from living organisms, and so is oil, but... solar power also, that is from the sun, and wind power, I think the sun might, like, heat up the air or something to make that happen, so I guess it's all from the sun.
Okay, actually, that's pretty good analysis. So this is supposed to say energy. It's kind of a pathetic energy. Okay. So plants also do cellular respiration. Sometimes we think of plants as just doing photosynthesis and animals doing cellular respiration, but the idea is...
that's how they get the energy back.
Right.
After they make it, they need to use energy.
Yes. Why would they make glucose if they weren't going to use it? So if you're doing the equation for cellular respiration...
Because they need to eat at night, that's the...
Yeah. Or when it's cloudy. Let's see, where is my eraser?
Or in the end of the world.
So if you're doing the equation... Why is that doing that?
That's huge.
You want to start again? That was kind of bad. Is that like a little one?
Yes, that's a little one. Ooh.
Okay, so I want to change the arrow this time. Yeah, that was sort of bad. I felt bad.
No, this is just a bit of lag.
H2. Okay, so cellular respiration will go the other way. So I'm going to draw the arrow in the opposite direction. And this time you don't get energy from the sun. This time you release ATP.
Oh, right. That's why we need to breathe, because we get all that oxygen.
We need to breathe to get the oxygen. Good. So this is our energy. So
and also to get rid of all the byproducts.
So you breathe to get oxygen and to get rid of CO2.
And H2, actually. We breathe out H2. Even though we probably could use that.
We use it for so many things.
We use it for, that's what we do the chemical reactions in, I think. But
it's true. Oh, man, you're going to do well in biology. Holy cow.
We still breathe it out anyway, though.
Do you know what combustion means?
That means, like, explosion or, like, yeah, pretty much.
Could be, but it also means burning. So you could combust really fast, and that would be an explosion. Yep, no, you're right. So the two ways that you add CO2 back to the environment are either cellular respiration or burning, combustion. Okay, so now we're going to get more complicated, because sometimes plants get eaten. And so here's the same picture with a few extra things. So the CO2 is taken up by the plants in photosynthesis, and it goes back into the atmosphere by cellular respiration. Sometimes the plants get eaten by animals, and they do cellular respiration. Sometimes they just die and they get broken down by decomposers. Animals can also get broken down by decomposers. Decomposers also send CO2 back into the environment. And then we could still have combustion in here somewhere too. We can add another arrow for that. Here's another picture. Oh, look, here's the combustion part added in. So yeah, so now we've added fossil fuels. So tell me the difference between decomposers.
I mentioned that 2 slides early. I'm a psychic.
That was pretty good, actually. So when plants or animals are squished underground for 1 million years or whatever, you make fossil fuels. What's a fossil fuel, Davey?
A fossil fuel is like petroleum or, coal, oil, that kind of. Actually,
beautiful.
Like those are all the things I don't really know. What else can we?
I think you got it. So
natural gas.
Natural gas, yeah, natural gases too. Yep. So with fossils, and when you burn fossil fuels, you add CO2 to the environment. So that's why we're having so much CO2 in the environment now, because we're not just doing this stuff, we're adding in this extra one, and we're burning a lot of fossil fuels. So if you think of every time you take a hot shower, or you have your home heated or air conditioned, or drive in a car, or anytime you buy anything, basically you're...
Or if you live in a perfect world where they have windmills and stuff like that, then you might not actually have to worry about this.
But
or after we run out of this stuff, because it's not going to be here forever.
Okay. Can you describe the greenhouse effect? This is a car, by the way.
Okay.
So, David, we go to the beach. That doesn't happen much, does it? So
no, no. We go to the supermarket a lot, though.
Okay, yeah. So, anyway, we go somewhere, and sun shines into the car, right?
Yes.
It's a beautiful day. What happens when we get out to the car?
Oh, it's all hot.
It's crazy, crazy hot. Do you know why?
It's because it can go in through because it's light, but once it gets inside, it's not light anymore. It's heat, so
nice.
It can't get back out.
Changes to infrared. Good. So all the heat just bounces around, and it gets hotter and hotter and hotter. CO2, along with things like
Which
methane.
Which is why people have like mirror-like things.
But yeah, sometimes. So the thing is, with the environment, here's the planet, and we've got this thin layer around it of atmosphere.
Oh, and at the poles, the atmosphere is actually disappearing.
The ozone is.
Oh, yeah.
So that's a different thing.
That's what I meant.
So the layer of CO2, we're getting more and more CO2, and actually we're getting a lot more methane too. And so that stuff is really good.
We're overproducing cows.
Yeah, well, that's part of it.
That's not really the main thing.
Yeah, it's not the main thing.
But that's still funny to mention, though.
A lot of it is when you harvest natural gas, I think. But anyway, you're adding all these fossil fuels around here, and that's doing the same thing. So
and the methane
when the light comes in, instead of bouncing out, some of it bounces around.
Yeah, it's a greenhouse gas because it acts like a greenhouse and keeps stuff in, just like you mentioned with the car.
Right. So if you have more greenhouse gases, you're going to get a hotter planet. So that's what's going on with that.
Which, if you evolve, isn't really that big of a problem, but we can't evolve this quickly because it's not supposed to happen this quickly.
Right. So there will probably be some extinction because.
But if we take like things from the desert and put them in like the poles, maybe, because we realize that we're going to completely and put them in the South Pole because we realize that we're completely destroying our planet, then maybe we might just.
All right. Same picture. This one's showing you the burning of fossil fuels. This arrow's showing you.
Oh wait, why does it matter about wood though? Because that was just in the atmosphere a bit ago, so it doesn't really.
It is, but if you deforest a whole huge area,
then that's a problem.
That's a problem.
I get it.
Okay. And then plus you also have runoff of soil and stuff, so that's a problem.
Yes, that is a problem.
Here's another picture adding the water part in. So if you have carbon dioxide, you don't really need to know this part, but if you have CO2 and you put it in water, H2O. You get carbonic acid.
Oh wait, is that what acid rain is? I think. Or, no, what's acid rain?
No, it's sulfuric acid and.
I remember we like. Oh no, it's not CO2. It's
H2SO4.
It's like there's a mosquito right there. Oh, is that? No, it's on the outside.
Okay, so you add these two together and you get H2.
H2.
Which is this, and then C.
H2.
And then how many O's would we have? Yep, O3. And
or so if it's an unbalanced.
It breaks apart into the hydrogen ion.
Actually, sometimes it can be unbalanced, and you can make like two of the same thing.
Anyway, this is the bicarbonate ion. It's the way your body stores, or it's the way your body moves carbon dioxide through your blood. It's also how it's stored in the ocean.
Sorry, can you say that again?
More than you need to know. This is the way that you store. This is the way that you transport carbon dioxide in your blood.
Oh, okay.
And also it's how it is here. But anyway, that's probably a little more than you need to know. Okay, I think.
Oh my gosh! Guess what?
Sorry.
Guess what year it is? It's the year 38. Well, I think it's 1000. I don't really know my numbers. 38. Yeah.
Bye.